So, mark the quiz. My favorite student. Good old Ann. I thought I was your favorite student. Well, okay. How much work? Number one, a force of blah, blah, blah needed to push a car across the lot. 2 students pushed the car 28 meters. How much work is done? Well, work equals force times distance. Are they pushing and is the car going in the same direction? I think so if I imagine it. So it's going to be 767 newtons times 28 meters. 767 newtons times 28 meters, and I get 21,500 joules of work. I'll go to 3 sig figs. Okay. Suppose they complete this task, 1 mark. Suppose they complete this task in 58 seconds. How much power? Well, power is work over time. So it's going to be 21,476 divided by 58 seconds. 370 watts of power. Not much. Some. What work is done by raising or lifting a 688 kilogram box 28 meters? Noah, when we lift something, which force are we doing work against? So this is going to be, you know what? It's mgh. It's mg, gravity times the height. And in fact, last day I told you that was also stored gravitational potential energy, because we said that energy is the ability to do work. So I'm giving you a little another way to think about this. It's going to be 688 times 9.8 times 2.8 meters. And I get 18,878.7. I'll go 18,900. Work joules. Again, 1 mark, half mark off if you forgot the units or got the wrong units. Suppose it does this in 73 seconds. How much? Well, power is work over time, which is going to be 18,878.72. divided by 73 seconds. 259 watts. Okay. Work, vector or scalar? Or you could write the word scalar. Work is measured in what units? Now, if you said Newton meter, I'd take that because it is force times distance. But yeah, we call that a joule. Power is measured in watt units. Now, you could say joules per second because it's work over time, but we've defined that as a watt. And then we turn the page. What's the minimum power generated by a 64 kilogram person who climbs 82 stairs? Each one has a height of 21 centimeters in 83 seconds. Okay, let's put it all together. Power equals work over time. Well, Oscar, I got that okay. Yay. How much work? Well, if you're climbing stairs, I think, Noah, that's also a lifting. I think it's going to be on the top, mgh. That's how much work she's doing. Which mass? 64. Which g? 9.8. Which height? Well, I think it's going to be 1 stair, which I got to change to meters, 0.21, times 82 stairs. That's the total height. 64 times 9.8. Am I wrong? I'm good, I hope. 130.1, 130 watts, I'll say. Is that right? 64 times 9.8 times 1 stair times 82 divided by 83. Mr. Dueck, that's not very much. Any of you ever tried, like at Science World or in some other sciencey place, pedaling a generator to try and light a light bulb? You've got to pedal pretty quick to get a light bulb to go. It's actually, we are not very efficient power producers as human beings. Okay, Danielle? Yep, okay. An electric motor lifts a load, a vertical distance of that. Okay, power, work over time. And Noah, you'll agree with me that when we're lifting, the work is mgh, the change in potential energy over time. Mass 25, G 9.8, H 24, all over 32. This might actually work out evenly. Let me see. Oh, not quite. 184 watts. Ah, how efficient is the motor? Well, efficiency is power out divided by power in. But Carson, really what I know, it's the smaller number divided by the bigger number. So I have this, you know what? It's going to be 184 divided by 244 times 100%, whatever the heck that is. 183.75, I'll use that, divided by 244 times 100. Looks like it's about 75% efficient. 75.3 if you really want to be fussy, but I'll just go 75% efficient. Which, by the way, tells me this is probably an electric motor, because electric motors are far more efficient than internal combustion gasoline motors. Gasoline motors are terribly inefficient. Number 8, this one was right from the notes, but this is a nasty. Okay. How much work did the, this I can do. Work equals force times distance, and they told me the force, 65, and they told me the distance, 14 meters. So the applied force did 910 joules of work. But some of that got bled off by friction as heat. How much work did friction do? Well, the work done by friction is going to be the force of friction times d. And really, I should do a good free body diagram. What are the forces? I have gravity down. I have normal force up. I have an applied force of 65, and I got a little friction. And I would say to myself, friction is what times what? Friction is what times what? Mu times the normal force. And now I have to go also times distance. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Kyle likes that little rant, does he? Okay. Mu mg times d, 0.25 times 12 times 9.8 times 14 Do you get 411.6? I'll write 412. Now, if you write that, Jules, if you write that, I'll give you full marks. But why is that technically wrong? Because it is. Why would it be negative? Because the distance and the force are in opposite directions. Yeah, so I'll put the negative there. I didn't really specify in this question a direction. What we're really saying is you lose that much energy to friction. So what's the net work done on the mass? It's 910 takeaway 412. It's 910 takeaway, and I'll use my answer button, 498 joules of work. Where did that work? Where did that energy go? That's the part that caused this box, this mass, to speed up. That got turned into kinetic. How do I know it's speeding up? Because there's an unbalanced force. So I think it's 1 mark for each of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, I guess I went 1 mark for each of these. Can you give yourself a lovely score out of, count them, 13, please? So let's continue from last day. What did we say? This was the law of conservation of energy, G. The amount of potential plus the amount of kinetic, initial and initial, have to equal the final amount of potential and the amount of kinetic. Or if we say to include friction, whatever's missing must have gone into heat, like burning the paper, smacking those spheres together. Where do we really use this? Oh, skiing and roller coasters. Skiing and roller coasters. Example 4. So here is the phrase that I tend to use in Physics 12. It says this: at location Z, a 72 kilogram skier is traveling at 18 meters per second. How high up the next slope can the skier reach? Look at the picture, look at the situation. Is there a change in height? Yes. Is there a change in speed? Yes. Is there a yucky, curvy path because of the hill? That's a job for conservation of energy, a scalar. Because especially those who take Physics 12 next year, you'll have a whole arsenal of tools in your physics toolbox. What do I use when? Well, there's a change in height, and a change in speed, and a yucky, curvy path. Try conservation of energy first. There may be other ways, but that's my starting point. So looking at this, is there a change in height, Noah? Say yes. Is there a change in speed? Is there a yucky, curvy path? Because otherwise we'd have to somehow take into account directions, which way is that? Blah, blah, blah. So I'm going to start out by going like this. Plus heat, yes or no? Why? Okay. And you know what? Snow's pretty good. Ice is even better, but yeah, snow is reasonably frictionless. Our answer will be close. Now remember, kinetic energy, that was the energy of what? I'm looking for a word that begins with the letter M and rhymes with lotion. Okay, the energy of motion. So when do you have kinetic energy? If you are moving. Ready? At location Z, right here, is the skier moving? So do they have kinetic energy? Then we're not going to cross that out. At the top of the hill, is the skier moving? In other words, my next step after writing down the law of conservation of energy is, which of these are 0? Now, potential energy, gravitational potential energy, that's due to your height. So at any of these situations, is this person at a height of 0? When? Initial or final? Once again, PEI gets hosed. That poor province. Oh, we all know it's not really a province anyways, right? Come on. An island, please. So what I end up with is this. A half mv initial squared, because kinetic energy is a half mv squared, and so kinetic energy initial will be a half mv initial squared. That has to equal, do you remember, mgh, and it's final, so it's going to be h final. Hey, is there an m in everything on the left? Is there an m in everything on the right? What does that mean? Okay, well, it means, first of all, it means mathematically they cancel. Here's what it really means. It means that when you're skiing, little kids can ski next to adults and they're not having to constantly adjust their speed. Doesn't matter whether you're an 8-year-old or a 40-year-old, you can ski next to each other. And it only comes down to skill level, but there's no physics reason that says somehow the adult has to be slowing down all the time, as long as we're frictionless. Now, if we do add friction, the M does not cancel, but is snow pretty frictionless? So you can ski kids and adults, heavy people and light people, with very little adjustment. I don't know if you ever wondered why that's the case. There's the physics of why that's the case. What are we trying to find here? Oh, H final? How would I get H final by itself, Spence? Oh, cool. So if I hear you correctly, and I think I do, you're saying this. The final height is going to be, there was a VI squared. What did you say to divide by? G. Now, look up for a sec, folks. Although you could put the 1/2 in front, I find it much cleaner, much tidier to just say, look, that's the same as putting a 2 down there. That looks much nicer. Yes? What was VI? 18 squared divided by 2, 9.8. How high up the hill will they go? You get, what, 16.5 meters? And then they'll start sliding back down because all of that potential wants to turn back into kinetic. Remember the skateboard park app that I showed you last time? Where you can really use this is, Natalia, roller coasters. Example 5. A roller coaster car travels as shown below. At point A, it is moving 12 meters per second. If we ignore friction, how fast will it be traveling when it reaches point B? Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. And I'm just so I can keep everything on one screen, I'm going to start doing my work in here instead of down there, just so I can get it all there. So I'm going to go A, KE initial, PE initial, KE final, PE final. Plus heat. Oh, no, A says if we ignore friction. Are any of these 0? At the top, am I stopped? Nope. At the bottom, am I stopped? Nope. In fact, what they want me to find is the speed at the bottom. At the top, am I on the ground? That doesn't make sense at all. At the bottom, am I on the ground? Oh, so this time PEI gets to stick around. Okay, fine. Technically, they're a province. Now what? Let's break these down. This is going to be a half m v initial squared m g h final equals a half m v final squared. Is that right? Oh, h initial. Thank you, thank you, thank you. Candy for Carson. You're right. Anyone notice anything else? The halves don't cancel because there's not a 1/2 in everything. But I'm going to show you a great trick to get rid of them without canceling. But there is something that does appear in everything. What? How many of you have been on a roller coaster before? Yeah? How many of you had to step on a scale before you got on the roller coaster so that we could carefully balance out things for safety? None of you? Why? What do you notice here? What cancels? The mass. I don't know if you ever asked yourself, why can we just casually get on a roller coaster? Shouldn't we have to like carefully put heavier people next to light people and make sure we don't have two really, really heavy people? No. Or let me ask you another question. Will an empty roller coaster make it through the track the same way as a full roller coaster? Yeah? Why? Masses cancel. So you can see when they test it, they can just send an empty coaster through. They don't have to put a bunch of guinea pigs. Now, if there is friction, if there was a little heat there, it's true the masses don't quite cancel. Oh, they grease those roller coasters down pretty good. They don't have friction to 0, but close enough that we can treat the masses as though they cancel. Now, Carson talked about the 1/2s. What are we trying to find? Okay, we're trying to get this by itself, and I got this. I'm going to show you a great trick. This is called clearing fractions. You may have seen it in high school. What I'm going to do is I'm going to times by 2 times by 2 times by 2. Now you'll notice I multiplied the second term by 2 even though there's no fraction. That's because if equation solving says you have to do the same thing to everything. You can't just magically put a 2 in there, but if I times everything by 2, I'm good. Now why is that so nice? Carson, what's 2 times a half? That cancels and that cancels. So I haven't exactly canceled out the halves. I've cleared them. But I do end up with 1 extra 2. But I would argue that this equation here is much nicer. Put your pencils down. You may recall somewhere around, I kid you not, Halloween Remembrance Day, I gave you this equation. Remember that one? And I told you that I would show you where it came from someday. Isn't that it? Because isn't G acceleration and isn't D? It pops out of this. But for me to have told you that way back in Remembrance Day would have terrified you with all these squareds and things kicking around. But it turns out that equation, which we have used, it's actually a variation. It pops out of the law of conservation of energy. Hashtag nerd trivia. Okay. Pick your pencils up, please. What are we trying to get by itself? Via, how to get rid of a squared. So it's going to be, don't want to erase it, Mr. Dueck. Square root. I'm running out of room, so now I'm going to move down to part A, but I think I can, you got the picture and everything together. So we have this, the final speed, and you'll notice I'm not putting vector arrows because this is scalar, not vector. This doesn't tell us the direction, although looking at the picture, I'm pretty sure the final speed is horizontal at the bottom there. But it's going to be the square root of VI 12 squared plus 2 times 9.8 times my initial height. If we're designing this roller coaster, how fast will it be going at the bottom of the hill? Probably want to make sure you can do this on your calculator. I'm going to type everything in the square root first, press equals, and then square root answer. So Noah, I'm going to go 12, hit my squared button, plus 2 times 9.8 times 18 equals, and then I'll go square root answer button. (22.3 meters per second), is that right? Okay. Are you ready? Let's do some thinking here. What if the hill was higher? What if the height was higher? Are you going to be traveling faster, slower, or the same when you get to the bottom? If this number got bigger, how would that affect this answer? Well, if this number got bigger, what would happen to the number inside the square root? Bigger. So when you take the square root, you're going to get a bigger answer. But it's not one-to-one. Twice as big here doesn't give you twice as big here. Twice as big here gives you the square root of twice as big. Which is why if you see roller coasters, there's a competition among amusement parks who's got the biggest, tallest, and fastest roller coaster. They're reaching their maximum point because building twice as high doesn't give you twice the speed. So you're only getting small increments of speed, and they're running into engineering challenges. It's only so high you can build with the current material before it gets unsafe. I think the current fastest roller coaster, it changes every couple of years. I know it was at Cedar Rapids in Ohio, but I think now it's in Japan. I think. B. Suppose the roller coaster, when it gets to the bottom, is only traveling at 15 meters per second, not 22.3. How much energy was lost to heat? Justin, what's this question wanting me to find? What kind of energy? Yeah. Hey, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? You know what this is a job for? Conservation of energy. Ah, are they talking about heat? So this time I'm going to go like this. KE initial plus PE initial equals KE final plus PE final plus heat. And the heat is the thing that I'm eventually going to get by itself. Are any of these zero? Are you ever stopped or on the ground? Which one? Stopped? Oh, when are you on the ground, initial or final? Justin, what did you say we're trying to find? Okay, I want to get the heat by itself, so I need to move this over. How? What's the KEF doing to the heat? Hey, what's sitting right there? Plus, so how will I move this over? Subtract. For some reason, on this equation, kids want to divide, and I don't know why, but it happens even with my physics 12s. Don't do that. It's subtract. I'm going to get this. Oh, you know what? Let's do heat in red, because, you know, fire, heat. It's going to be kinetic initial and potential initial. Those just drop down like dominoes. Minus kinetic final. Is that okay, Amy? Let's break these up even more. So heat is going to be a half mv initial squared plus mgh initial minus a half mv final squared. I don't need to cancel the halves this time because there's no half in heat. I'm happy with this. What will I type on my calculator for a 1/2? 0.5. Or I can use my fraction button, 1 fraction, or what. Anyways, do the masses cancel this time? Is there an m in everything? Wait a minute, I thought there... Oh! Which term does not have an m in it? Heat. Now, what causes heat? It's a force that begins with letter F. Friction. So, in real life, the masses don't cancel. But again, Colin, if I grease my roller coaster really well, I can get my friction down to near zero. And that's why, and maybe you never thought about why, but I'm a nerd, I think about these things. You don't have to step on a scale before you get onto a roller coaster. Otherwise, they'd have to. Now, how many of you were ever on the Wild Mouse? It's not at P&E anymore, but it used to be there. Terrifying ride. Okay? For 2 reasons. First of all, the ride itself. But did you ever look inside the cars at your feet? You ever notice this, eh? There's sandbags in there for ballast. And I know intellectually here the masses cancel. And so I've tried to figure out with that ride, A, why they don't seem to cancel, and B, how they found out that the masses don't cancel. And I hope they didn't find out the hard way. But I don't know if you ever, that ride, there was sandbags in the bottom, by your, especially if you're sitting in the front, by your front feet. There was sandbags there. I don't know why. So for me, it was doubly terrifying, the ride and the fact that I knew something wonky was going on that I still haven't wrapped my brain around. Okay. Hey, plug and chug, Justin. Heat equals 0.5. Justin, did I tell you the mass? I've scrolled down. I think I gave you the mass of the roller coaster in the original question. Did I not? Yeah. What? I didn't hear. Sorry? 245? And then what was my initial speed, Justin? I think that's also in the picture, I hope. 12. And most common mistake, folks, don't forget the squared. Plus... What'd you say the mass was? What's G? Good old. What's G? 9.8. And I've scrolled down. Keep going. What was the initial height of the hill? Sorry? 18. Takeaway, 0.5. You said the mass was 245. Now, in part B, what did I say our final speed was? Part B, just read. What is our final speed? Yeah. 15 what squared? Okay, folks, get your... This is straight plug and chug, no square root, nothing. You should be able to just type this in and go. How much energy was transformed into heat? And sound and other dissipative energies, but I usually just kind of categorize that all as heat. He's getting his calculator out. Excellent. It's also good practice because, you know, this is long but not tough. See, you should be able to type this all in one line. I have 245. I have a feeling it's going to be in the thousands, maybe in the tens of thousands. I'm doing the math really quickly in my head, roughly. That would have been a problem. Do you get that? 33,300? No? You got that? Thumbs up? Yeah? Okay. I think the group consensus is, by the way, these are complicated enough. We'll do a group consensus because I don't preview these answer keys. Yeah, 33,200. I'll go 33,300. Units, heat. Heat is a form of energy. Energy is measured in joules. Put your pencils down. Look up. This is the other reason conservation of energy is so nice. Energy is a scalar. Energy is a scalar. Energy is a scalar. And what that means, Thomas, is it doesn't care about the path. It only cares about before and after. What if I had given you the roller coaster, but instead I had drawn it like that? You'd get the same answer. You'll get the same 22.3. What if instead I had drawn the roller coaster like this? If we ignore friction, you'll get the same answer, 22.3. In fact, what if for some reason, Thomas, I had dug a tunnel into the ground and then come up? I'm telling you, whatever speed you gained going lower, you'd lose exactly that same amount getting back, and you'd still end up at 22.3. And this is why work and energy are such nice concepts to deal with. They let you look at really complicated situations where if we tried to do them with D equals VIT, VF, the vector stuff, and forces, it'd be a little ugly. Example 6. A 25 kilogram object is dropped from a height of 42 meters and it lands in the snow with a speed of 25 meters per second. How much heat energy was produced during the fall? Oscar, what's this question asking me to find? So that alone suggests maybe conservation of energy. Is there a change in height in this question? Dropped. Is there a change in speed? Yep. Now, is there a yucky, curvy path? No, but the fact that it talks about heat energy, I'm going to try solving this with energies first. Certainly, if there was also a yucky, curvy path, absolutely. So, the law of conservation of energy. Kinetic initial. Potential initial. Kinetic final. Potential final. Oh, this time I'm going to add plus heat, because they're talking about heat energy. In fact, what did you tell me they're asking me to find? Okay, I can do this. Now, before we go further, let's ask, are any of these zero? Let's look at potential energy. Are we ever on the ground? At the beginning, initial, or at the final end? So I can certainly do, because mg, h, if h is 0, is 0. What about kinetic? Are we ever stopped? Do you recall way back when, also from around Remembrance Day, I told you if I say the word dropped, what can we assume VI is? What did you say they're asking me to find? How would I get the heat by itself? Subtract what? So I want this to stay. Subtract that over. And I'll get this. PE initial minus KE final. That equals heat. In fact, I'll get heat equals, what was PEI? Not a province, it's a formula. What was PEI? Potential, and oh, that was going to be mgh, and I guess initial means initial, minus, and what was the equation for kinetic energy? A half mv, which v? Final, squared. All right, plug and chug. Oscar, did they give me the mass? Oh, masses don't cancel here because no mass in heat. Did they give me the mass? What? G, 9.8. What's my initial height? 42. Minus a half. You said M was 25. What's my final impact speed? That's after impact. What's my final impact speed? Yeah. And I've already decided next year I'm not going to use 25 for the mass and the speed. That's confusing. I'll change this next year. Anyways. How many joules of heat? I think, is Tarzan the last one? Yep. Okay. Good. 25 times 9.8 times 42 minus 0.5 times... Is it 25 squared? Yes, it is, Mr. Dueck. That's... Do you get that? 2,480. By the way, I mean, we're getting towards the end of the year. How many sig figs? This number here? 3. How many sig figs? Technically, I should go to 2 sig figs, so it would technically be 2,500, but I'm not being fussy on that, so we're going to go 2,480 joules. How many of you ever got on a rope swing before? Was that a hand up? Colin? No. Now, I did not grow up in Maple Ridge Pit Meadows. Is there somewhere where there's a good rope swing over a lake that kids know about? No? Okay. Is there one in Pitt Lake somewhere? Okay. Because there used to be, I used to work at a summer camp in Hope, and on Kakawa Lake, there was actually a really nice tree that overhang, and someone had actually mounted a water ski handle. It was a good rope swing, and it was about 50 feet deep right where the drop-off went straight down. It was a very, very good rope swings. Rope swings. Okay? Tarzan weighs 82 kilograms and can run at 8 meters per second. He runs along the ground, and then he grabs the vine, and as he grabs the vine, he lifts his feet up so he swings into the air. What maximum height does he reach? Kyle, is there a change in height in this question? Yeah. Is there a change in speed? Yeah. Is there a yucky, curvy path? You need to imagine how, you know what this is a job for? Conservation of energy. Rope swings are great examples. I should also say, I'm an amusement park ride nut. There's absolutely going to be a roller coaster question on your test. So I should have said back here, not just, I like this question, I like this question, I like this question. What I should have said is, example 5, will you marry me? That's what I should have said. Okay. Now I can ask you really 2 things. I can either say, how fast are you going at the bottom if I tell you how high the first hill is? Or I can tell you how high the first hill is. Or I can tell you how fast you are going at the bottom and tell me how high the first hill is. You're either going to find this or speed at the bottom. Or heat. Anyways, Tarzan. Okay. Plus heat, doesn't mention it. Are any of these 0? Let's look at the speeds. So we're talking about a rope swing, and I guess what we're talking about then is starting out at a speed, and how high can you go? Was there any of those situations where the speed was 0? Initial or final, or neither? Okay, so he's running, he's starting out how fast here? He has to have some speed, otherwise he's not going to swing. So I don't think initial speed is 0. But at the top of a swing for a split second, how fast will he be traveling? Okay, so we can say this. Potential energy. Is he ever on the ground? Well, this is where technically no, because his feet are on the ground and he's not grabbing the rope swing with his feet. You with me? But this is why conservation of energy, Thomas, is so beautiful. It's a scalar. It doesn't care about the pathway. In fact, you can put the ground wherever you want to. So don't write this down because I'm going to draw a terrible picture. Here's the rope swing. There's the handle. Here's Tarzan running, about to grab the rope swing. Even though the ground is right there, I'm going to put the ground there, and mathematically we'll completely get the right answer, as long as we can put ground 0 wherever we want. Why? Because conservation of energy is a scalar and lets us be really sloppy, actually lets us be really clever. So, is he starting out on the ground? Technically no, but in my conservation of energy, PEI gets it again. Gets hosed again. Those poor people with their fake province. What was the equation for kinetic energy? Right? What was the equation for potential energy? Oh! Anybody notice anything? What was that? Okay. Although I told you Tarzan's mass is not necessary. So, you ready? Here's our thought experiment. Suppose this vine was really strong. Let's make it out of somehow some titanium Kevlar unbreakable alloy. Not only could Tarzan swing on it, but if Tantor the elephant came running and grabbed this vine at 8 meters per second, he would swing out exactly the same height as Tarzan. Do you know how I know? Masses cancel. Okay? Masses cancel. That's kind of neat. What are we trying to find? Hey, you know what? We've seen this one before. Get the H final by itself. In fact, Spencer, I think you were the one that told us this one last time, so I'll go back to you. How do I get the H final by itself? Divide by G. In fact, this is where I gave you that cleaner version of the equation. I said it's VI squared divided by G, and I said, yeah, you can times by a half, but that's just the same as sticking a 2 in the bottom there. 8 squared divided by 2 times 9.8. Oop, wrong button. 8 squared divided by bracket 2 times 9.8. 3.3 meters high. This also explains swinging. You've all been on a swing set before? Yep. Have I finished the lesson yet? Sit down. Patience. Have you been on a swing before? How do you get yourself to go higher on a swing? You all figured this out when you're about 4 years old. What do? What you're really doing by shifting your weight and tucking your leg, you are adding energy to the system. And you're adding kinetic energy if you time it just right. And what does that kinetic energy get turned into at the top of each swing? A little bit more potential, a little bit more height. Oh, and on a swing, also mass cancels, which is why it still works for you guys if you go to a swing now, even though you're much bigger than you were when you're 4. The same systems to work. All it comes down to is, can the chains hold it or not? Okay, rope swings. What's your homework? Number 1 is good, number 2 is good. Four is good. Five. 6. You can tell I typed this up back when Pitt Meadows had a track. I need to change that and make it the field. Actually, no, I wouldn't launch a rocket on the field because that would damage the artificial turf. 7. Okay, and then part 2, number 1 is good. Part 2, number 2 is good. Part 3. Now, number 3, the final height is 2/3 of the way down the ramp. What's the height of the ramp? 60. What's 2/3 of the way down? What's 1/3 of 60? 20. So your final height, that's your final. Not 0, sorry, but okay. Number 4, ask me about that one next class. Need to nuke number 6, sorry, note to self. 7 is good. And we'll pause there.